Okay, let's start. Good morning. Today we are going to go to second order phase transition. Goes back to 1920s. The problem is given by Wilhelm Lenz to Ernst Ising or Ising. As a PhD thesis, and Ising was able to solve it in one dimension, and he found no phase transitions. So it was a disappointment on his part. But in 1946, 2D case, this is, let's call it one-dimensional, 1946, Lars Onsager solved the 2D case, and he found a phase transition. So there was a success. 3D case is not solved yet exactly. But it is solved numerically. So you can solve it. If you can, you'll be famous, I think. Well, it is a lattice model. So you put the spins on a lattice. So that means magnetic moments at lattice points at fixed sides. And in this model, they are represented by shear numbers. Okay. Interactions are taken between nearest neighbors only. So that's the model. Well, in a pictorial way, here's the model. This is Ising. Well, you can do this for spins. isn't it? Instead of numbers, positive, negative numbers, it can represent a spin system, or it can represent a binary alloy. Here are the atom types. So model is really very useful. Or it can represent a lattice gas. Lattice gas is something like this. Lattice gas. So, you see, a collection of numbers can correspond to different physical systems, and this model is quite useful in that sense. In a one-dimensional case, where Ising was successful in solving, you can have the following thing. Here are the lattice sides. You can put spins there. Etc. Now you can apply a magnetic field if you like. So, originally it is introduced to solve the ferromagnetic problem, ferromagnetism, which is of course caused by spin-spin interaction, very strong interaction, and phase transition is of second order type. So we are doing now strong interactions between particles, unlike the ones that we have studied up to now. And the corresponding phase transition is of second order. So it's continuous. There are, of course, elaborations on this model. There are lots of related models in statistical mechanics. Here is a list, partial list. Well, related models, Ising-like models. Potts model. Well, here the numbers may take several values. Have several values, not only two, up, down, plus or minus. Heisenberg model is another one. Well, you have a vector interaction Hamiltonian is written as Ij nearest neighbors Si dot Sj. So it's not only up and down, can be more realistic, decorated models. Well, we have several sublattices. Instead of one lattice like this, we can have more complicated geometry. You can introduce complex lattices like FCC, BCC, or introduce long-range interactions. So that this interaction parameter can be a function of position. And of course, you can have random J interaction. This gives you a possibility for glass theory. You can also make it time dependent, the whole theory. You can study kinetics. So it can be made quite rich. Now, if you remember the ferromagnetism, you see there are two important factors. One is the temperature, which is trying to kill the magnetism, and the other one is the magnetic field, which is trying to establish it, or spin interactions, in this case, trying to establish the ferromagnetism. So, well, entropy wants spins to be disoriented. Spin-spin interaction energy but this is a strong thing in this case. It wants spins to be parallel. So there are two competing effects. Well, temperature, of course, is a disordering effect, killing magnetism. but spin-spin interaction energy is trying to lock the spins at the same direction. So at large temperatures, entropy wins. So you have a magnetization which is 0. At low temperatures, energy wins, spin-spin interaction energy. And you have magnetization. And in this case, there is a critical temperature at which you start having the magnetization. As you remember, something like this. That is the critical temperature, M. You start having the magnetization. Now we have several methods of calculation of this model. One-dimensional model can be solved exactly. So let's see that. Methods of calculation. Exact calculations. One dimension is quite easy. This is done by Ising. Two-dimensional is done in zero field by Onsager, as I already told you. 3D not available yet. So here's a problem where you can solve this. If you do, and of course, there's always numerical solutions, so well, there's also calculations at high temperatures, high T and low T expansions. So you can do calculations in these limits. You can also do a mean field theory. And of course, there is lambda approach. And finally, we can include the computer simulations. Okay. I know people who are doing computer simulations all their life for different dimensions, and they are getting approximate solutions. Those are the approaches to this model, so you can choose. I will do the one-dimensional calculation now. 2D, well, this is done in in your book as one chapter, and also in Huang's book, exactly, it took 20 pages or so. Okay? So I'm not going to do it exactly, but just sketch you the important steps and the result of the calculation. Okay? That's what I'm going to do now. Then I will tell you something about mean field and lambda approach. That's the program for today. It's extremely useful model, and I have seen research done on Ising model trying to represent the nerve cells, the passage of sodium, potassium through the nerve cells, membranes. So it is quite a famous and useful model. So our aim once more is to understand ferromagnetism. Strong spin-spin interactions, locking spins in the same direction, creating domains. So if you apply a magnetic field, you can hear the sound that these domains are going to be aligned with the field and creating very strong magnetism. Okay? That's the aim. Now let's do the one-dimensional calculation, exactly solvable, and as I told you, there is no phase transition in that case. So Ising was very unhappy to find that result and leave the field forever. And we had to wait for Lars Olsager to solve the two-dimensional case with a phase transition, second order phase transition, 1946. Okay, let's see the model. One-dimensional Ising model. An exact solution. The Hamiltonian can be written as, well, usually, as I told you in my first lectures, statistical mechanics is model dependent. So this is a model for interactions between spins. In one dimension, you can write the interaction as an interaction parameter, J, and sum over spins, N of them, and the field term, applied field, it is that simple to write. This is spin-spin interaction, isn't it? With the interaction parameter J, and this is the field term, minus mu dot H, as you know. So here sigma are just numbers. Well, you can write this in more symmetrical form. As follows, minus J, sum sigma I plus 1 minus H over 2 sigma I plus sigma I plus 1. Here we are going to use periodic boundary conditions. So instead of having a straight lattice, we can have something like this. So the n is coinciding with 1. Okay? So sigma n plus 1 becomes sigma 1. You can join the n's to get this periodic condition into your problem. Now, as I told you, in this model, sigmas are just numbers. So it is plus 1 for up spin, minus 1 for down spin. Just numbers. So how can that term favors spins to be in the same direction? Interaction favors the spin in the same direction. For this, you have to have J positive number, isn't it? If J is positive, then when these are in the same direction, plus 1, for example, or minus 1, multiplication gives you positive 1, so the whole energy is negative, which is favorable, lower energy. If J is negative, of course, this then becomes a positive number, so that favors opposite spins, spins to be aligned in the opposite direction. Only in that case, this is minus 1. That is a positive number, so you have a lower energy for opposite spins. So this favors spins to be parallel spins. That thing favors anti-parallel spins. So that corresponds to ferromagnetism, and negative J corresponds to anti-ferromagnetism. Is this clear? Okay. Now, with this Hamiltonian, we are in a position to solve the model to get the result and see if we have any phase transition. Of course, I told you the result right at the beginning that we are not going to find any phase transition in this one dimension. But let's see that. Let's write the partition function using this Hamiltonian. Well, trace e to the minus beta h, isn't it? That's the canonical approach. But when you write this, you get the following. The Hamiltonian in a symmetric form, sum okay. Now we can write this by using a very nice transfer matrix which is introduced around 1941. So it is a recent thing. Let's introduce the transfer matrix to make the calculation easy. Whose elements are going to be defined as follows. The matrix elements are just that. So kind of related to our problem, isn't it? So explicitly, if you want to write the matrix elements up spin, that becomes e to the beta j plus h. If you put 1 for each, you have j, you have 2, divided by 2 is 1, so that's the result. If you have -1 and -1 down spins, the matrix element becomes e to the beta j minus h, because that is -2 in that case. Very simple. And off-diagonal terms are equal and it is e to the minus beta j. If they are plus and minus 1, that's minus, and this is 0, isn't it? So that's very simple. Now, the beauty of this is that you can write this partition function, well, instead of Vt, I have to write Ht, isn't it? I have magnetic field in my problem. So then this partition function becomes, for n spins under magnetic field and with temperature, becomes, the summations remain but those terms turn into this. Very nice. So transfer matrix is transferring you from one spin to another, isn't it? So that goes all the way to sigma n, back to sigma 1. Okay? Very well defined matrix. And when put it into a matrix form, we know how to solve problems. You just diagonalize. Okay? So this thing can also be written as a sum over spin sigma t to the n sigma. each sum, okay, is a unity operator when you took it. And that gives you well, this is nothing but the trace of transfer matrix to the power n. You have n spins. Huh? Very nice object. I think you should know that. And since we are dealing with a 2 by 2 matrix, you can have two roots to the power n, larger root and smaller root, larger or smaller eigenvalues of t, eigenvalues of t, and if you write the matrix T explicitly, I have written for you the matrix elements, so you have the following transfer matrix. J plus H, e to the minus beta J, e to the minus beta J, and e to the J minus H, isn't it? That's your matrix. So, to get the eigenvalues, we can diagonalize this matrix, and eigenvalues of the matrix satisfy the following equation. Solving or diagonalizing a matrix means finding that determinant with identity matrix and putting it equal to 0, isn't it? That's the way to calculate, find the eigenvalues. And if we do that, we find the following eigenvalues, lambda plus and lambda minus. Straightforward. Here is the solution. That is the solution. Okay? You can do that yourself. Put the determinant equal to 0 and solve. That's what you find. And for n going to infinity, need to keep only the larger eigenvalue. That's the limit of interest in our case. Many spins in the problem. It is solved. Now we can calculate Helmholtz free energy per spin. Well, free energy per spin. To get the thermodynamics of this, or AHT, is nothing but minus kBT ln of lambda plus So if you call this smaller FHT, we have minus J minus KBT ln of cosine hyperbolic beta H plus this square root. Square root is the sinh square e to the minus 4 beta J. Okay? From here, we can go to magnetization. That's our aim. Magnetization per spin so I am telling you explicitly the steps to get to the question of interest. Del F, del H, constant T. So that gives us the magnetization, and of course we hope to find something even at H goes 0, isn't it? When the external field is 0, we should have a solution. And this gives magnetization per spin as sinus hyperbolic beta H plus sinus hyperbolic beta H times cosine hyperbolic beta H divided by D, all divided by, so cosine hyperbolic beta H plus D, where this D is the square root, you remember, beta H plus e to the minus 4 beta J, square root power 1/2. As you can see from here, we are having a problem. When you put the external field 0, this is the test whether we have magnetization or not. This goes to 0. There's no magnetization. So no spontaneous magnetization. Well, these go, sinus hyperbolic 0 is 0. So no spontaneous magnetization except at t equals 0. Well, t equals 0 is not available, we cannot reach there, so that means there's no ferromagnetic transition. So, no ferromagnetic transition. That is the disappointment, okay? We need to have magnetization even in the absence of the magnetic field in a spontaneous manner to have ferromagnetism. Okay? In this case, we don't have it. That was the disappointment for Ernst Ising. Unfortunately, he didn't try the two-dimensional case. Let's give a break. Do you have any questions with this? It's a very simple solution, nice solution, exact solution, and no ferromagnetic transition.